In this section, we're going to talk about antiderivatives. Alright, so the goal of the rest of this chapter is to learn some basic techniques for finding a function given its derivative. So, in other words, we're going to go backwards. So, find a function f whose derivative is given. So, let's say that the derivative is 2x. So the original function is actually x squared. And you can check to see that the derivative of x squared is 2x. Alright, so if the derivative is 3x squared, then the original function would be x to the third, because the derivative of x to the third is 3x squared. And in C, if the derivative is x to the third, well, I think the real issue for all of you is that these two up here had the number in front. Alright, so this one did not. So the original function is going to be 1/4 x to the fourth. And then I think if you're going to check this, you can see that this derivative of 1/4 x to the fourth would actually indeed be x to the third. And then we have this last one down here. If the derivative is 1 over x squared, or if this is actually x to the negative second, then the original function would actually be x to the negative 1 over negative 1, or just negative 1 over x. Alright, and you can check to see that that would be the derivative of negative 1 over x. Alright, so let me actually clear all of this off the screen here and go down a little bit so that we can do the rest of this page real quickly. And I don't know where that went. Alright, so now show that g of x equals 5x minus x squared over 2 is an antiderivative of 5 minus x. So this right here is the antiderivative, and this is actually the derivative. Alright, so all we have to do is actually find out what the derivative is and verify that this is true. So g prime of x is actually the derivative of 5x is 5, and then we have minus a half times the derivative of x squared, which is 2x, and that just ends up being 5 minus x. So actually this is verified. And that is the end of page 140. Alright, in this video we're going to talk about antiderivatives. So a function g is an antiderivative of a function f on a set of numbers I if the g prime of x, the derivative, equals f of x hold for every value of x in that set of numbers I. So the procedure of finding antiderivatives is called anti-differentiation or indefinite integration. And so now we have some notation here. Y equals, and this is actually the integral symbol. Alright, so if you thought that was a squiggly line or S in the past, it's actually the integral symbol. And this integral of f of x dx is going to be equal to g of x plus c. So what you need to remember is f of x dx is the differential, and that's what we talked about in section 4.1, right? So this is differential corresponding to g of x. So this is why we needed to talk about differential before we talked about anything else. So this is where c denotes an arbitrary constant, which means that the function g is an antiderivative of the function f, so that g prime of x is equal to f of x hold for all values of x in the domain of f. Alright, so given that g of x is equal to x to the fourth plus 2x to the third minus x is an antiderivative of f of x equals 4x to the third plus 6x squared minus 1, find all, that is the key word, all antiderivatives of f. So this is the antiderivative. Alright, just to be clear one more time, this is the antiderivative and this is the derivative. Alright, so let's just call this h of x. Well, we're not going to need h quite yet. But we need to actually find, alright, g prime of x. Alright, so g prime of x is actually 4x cubed plus 6x squared minus 1. And that happens to be f of x. Alright, just so we're all clear on something. Now, that means that h of x is going to be x to the fourth and then plus 2x to the third minus x and then plus c, where c is any constant. Now, why do we need that plus c? Well, let's take the derivative of this, alright? If we take the derivative of this, we have 4x to the third plus 6x squared minus 1, but the derivative of a constant c is 0. So the whole point is that we could add any number to this h of x and still get the same derivative. That's very interesting. I hope that you agree with that. We'll do a couple of more examples in the next video. In this video, we're going to finish page 141. So verify each of the given equations. Alright, so we have the integral of the fourth root of x to the third plus 1 dx is equal to 4/7 x to the 7/4 plus x plus c. Alright, so all we're going to do is find the derivative with respect to x of the 4/7 x to 7/4 plus x plus c and see if it gives us this derivative that's inside here. Okay, so let's see, this is going to be 4/7 times 7/4 and then x to the 3/4, and the derivative of x is 1, so plus 1, and the derivative of c is 0. And so now we have, well, the 7's and the 4's cancel, so we have x to the 3/4 plus 1, and that ends up being the fourth root of x to the third plus 1. So this is actually indeed verified. Alright, so now let's do the same thing for part B right now. The derivative with respect to x of this antiderivative here, alright, the answer to this problem, negative 1 over x minus 1 over x squared plus 1 over x to the third plus c. And, well, by the way, this is just actually, if it makes it easier for you, negative x to the negative 1 minus x to the negative 2 plus x to the negative 3 plus c. So this is going to be negative times negative 1 x to the negative 2 minus negative 2 x to the negative 3 minus 3 x to the negative 4, and then the derivative of c is 0. So this is actually x to the negative 2 plus 2 x to the negative 3 minus 3 x to the negative 4, or 1 over x squared plus 2 over x to the third minus 3 over x to the fourth. And, well, if I find a common denominator, I multiply this by x squared over x squared and this by x over x. So this just ends up being x squared plus 2x minus 3 over x to the fourth, which is what I want it to verify right here, right? Alright, so let's do one last one right here. So we have the derivative with respect to t this time of the answer, the antiderivative, t to the third over 3 plus cosine of t plus c, and then this derivative is actually 1/3 times 3t squared, and the derivative of cosine of t is minus sine of t, and the derivative of c is 0. So the 3's cancel, so this is actually t squared minus sine of t. And so there we have verified that as well. And that is the end of this video, but I hope that it makes sense how you would verify these integrals. This page 142 lists some of the basic rules for anti-differentiation. So these are just essentially rules that you are going to need to memorize. So I hope that you take this page seriously and memorize all of these as quickly as possible. With that being said, I want to do a couple of examples of applying these rules so that you can see how they're actually used in action here. So here we have an example that says evaluate each antiderivative or indefinite integral. So we have the integral of 2x plus 1 dx. So one of the rules, Rule 3, says that we can split this up into the sum of two separate integrals. So here we have integral of 2x dx plus integral of 1 dx. And then if we look at rule, so that's by Rule 3, if you're wondering where I'm getting that from. And then by Rule 2, we can actually pull this 2 out in front. So we actually have 2 integral of x dx plus integral of actually just 1 dx. So that's by Rule 2. Now, I'm going to write this x right here as just x to the first power dx. Alright. Now, the reason why I want to do that is so that I can actually apply Rule 1. Now, remember, in this chapter, we're working backwards from actually finding derivatives. So, I want to find the antiderivative of x to the first. And remember, x is actually the derivative. So, this is going to be adding 1 back to the exponent and then dividing by that new exponent. Alright, so remember the rule was, say, x to the n dx is actually x to the n plus 1 over n plus 1 plus c, right? So if we have x squared dx, then n was 2, so we have actually 2 plus 1 over 2 plus 1, or x to the third over 3. But if we just had actually x to the first dx like we did here, then that would be x to the 1 plus 1 over, let's see, 1 plus 1 is x squared over 2. So I hope that you sort of, after seeing two of these like this, you see that there's going to be a pattern to this that you're going to want to try to pick up on as well. And so then we have plus c, and this is just giving you c1 because it's actually the first, all of these are actually plus c, but a lot of times we'll find out later that we don't need that. But this is c1 for this first integral right here. And then we have the integral of 1 dx, and that's actually just going to be x. And then we know that the derivative of x of 1, so we can actually verify all of this, alright? And then plus c2, because this is the second integral right here. So the 2's cancel here. So we have x squared plus, and then we have an x, and then plus a c1 plus a c2, or we just write it as x squared plus x plus c. And really, this is just c1 plus c2, where c is equal to c1 plus c2. But if you just write plus c, I'll know exactly what you're talking about. Alright, so that is it for this video. I think that once you see a few more of these, it might make a little bit more sense. But just try to, again, get used to the rules at the top of this page. In this video, we're going to do page 143. So we need to find the integral of 8x to the third minus 9x squared plus 4 dx. Alright, so this is going to be broken up into 8 integral of x cubed dx minus 9 integral of x squared dx plus integral of 4 dx. So this is very similar to the last problem. Alright, so now using the rules that we had on the last page, this will be 8 times x to the fourth over 4 plus a c1 minus 9 x to the third over 3 plus a c2 plus a 4x plus a c3. Then we'll write all of the x terms together, but let's simplify that a little bit more. 8 over 4, 2x to the 4th plus c1. 9 over 3 is 3x to the 3rd plus c2 plus 4x plus c3. And then write all of the x terms together. So that's 2x to the 4th minus 3x to the 3rd plus 4x, and then plus c1 plus c2 plus c3, or as I mentioned before, you can just write it as a plus c, one big C at the end. Alright, so let's move on to the next problem here. This is integral of x squared plus 2x minus 3 over x to the 4th dx, and I'm going to actually rewrite that as x squared over x to the 4th dx plus integral of 2x over x to the 4th dx, and then plus integral of negative 3 over x to the 4th dx. So then I can pull out all the constant, but maybe simplify that a little bit first. This is integral of 1 over x squared dx, and then this is going to be 2 over x to the 3rd dx, and this one is just going to still be minus 3 over x to the 4th dx. Alright, so let's make this a little bit even more obvious than that, and this is going to be integral of x to negative 2 dx, and then integral of 2x to negative 3 dx, and then integral of negative 3x to negative 4 dx. And now I can actually simplify this even further and pull the 2 out of this integral and pull the minus 3 out of this integral. And now I'm going to use rule 1 to find all of these integrals here. Now remember, the rule says to add 1 to the exponent and then divide by the new exponent. See how this one went from 3 to 4 and this one went from 2 to 3? Right, so this is going to go from negative 2 up to negative 1. So x to negative 1 over negative 1 plus 2 times x to negative 2 over negative 2, and then minus 3 x to the negative 3 over negative 3, and then we'll just put a plus c at the end. That will make it a lot easier, and then we'll write this all without negative exponents. So it's negative 1 over x, and then the 2's cancel, so minus 1 over x squared, and then the 3's cancel actually, the negative 3's in fact, and this is plus 1 over x to the 3rd plus c. And that is actually the end of this video. We'll do the next 2 problems in the next video. In this video we're going to finish page 143. So let's do example D. The integral of the square root of x plus 1 over x squared dx. So I'm going to write that as the integral of x to the 1/2 plus x to negative 2 and then dx. Alright, so then I can split this up into 2 integrals. Integral of x to 1/2 dx plus integral of x to negative 2 dx. And then I'll just apply the same rules that I've been applying, adding 1 to the exponent dividing by the new exponent. So this is actually x to 3/2 divided by 3/2, and then that's going to be plus x to negative 1 divided by negative 1 plus a c at the end. And then if dividing by negative 3/2, by 3/2 is the same as multiplying by 2/3, so 2/3 x to 3/2 minus x to negative 1 plus c, or just 2/3 x to 3/2 minus 1 over x plus c. Alright, so now let's try example E here, integral of cosine x minus sine x dx. So that is all from that list of rules that you will need to memorize. So let's make this into integral of cosine x dx minus integral of sine x dx. Now remember, this is just undoing the differentiation or going backwards. So the integral of cosine of x will be sine of x, because the derivative of sine of x is cosine of x, alright, plus c1, and then minus the the antiderivative sine of x is negative cosine of x, because the derivative of negative cosine of x would be actually sine of x and then plus a c2 here, or that just ends up being sine of x plus cosine of x and then plus a c at the end. And that is the end of page 143. I have great news. On this page we're going to do a couple more examples involving trigonometric functions. So f, integral of secant of theta times tangent of theta minus secant of theta d theta. Alright, so I'm going to distribute this secant of theta. So I have integral of secant theta tangent theta d theta, and then minus integral of secant squared theta d theta. And then if I use the integration rules, the antiderivative rules that you should try to memorize still, this is going to be just secant of theta and then minus tangent of theta plus c. Alright, that's all based off of the rules that you're going to need to memorize. Alright, let's try g. This is actually going to be integral of sine of x over cosine squared x dx, because 1 minus sine squared x is cosine squared x. And then we'll break this up into integral of 1 over cosine of x times sine of x over cosine of x dx, because that's still sine of x over cosine squared x. Cosine x times cosine x is cosine squared x. And 1 over cosine of x is secant of x, and sine of x over cosine of x is tangent of x dx. And by the integral rules, the integral of secant x tangent x is just secant of x plus c. Alright, I'll give you a minute to write that down, but then we're going to move on to the application problem. Alright, so now I'm going to actually scroll down so we can do the application problem right now. I don't know why it's scrolling so fast and then all of a sudden so slow, but an evergreen nursery usually sells a certain shrub after 6 years of growth and shaping. The growth rate during these 6 years is approximated by dh dt is 1.5 plus t, where t is the time in years and h is the height in centimeters. The seedlings are 12 centimeters tall when planted. That's when t is equal to 0. Find the height after t years. Alright, well, you know that h prime of t is actually dh dt, and that was 1.5 plus t. So we want the height after t years. That is h of t. So that is just going to be the integral of h prime of t dt, or the integral of the 1.5 plus t dt. So that's integral of 1.5 dt plus integral of t dt. So the integral of the 1.5 is 1.5t, and the integral of the t is actually t squared over 2. So you should be getting used to these rules a little bit by now. And then plus c. But we can actually figure out what c is in this particular case. We haven't been able to so far, but in this case we can, because we know that when t is 0, that this whole thing is actually equal to 12 centimeters. So we're going to set that equal to the 12 centimeters. And so if this is actually, if we're replacing this t with 0, we actually have 1.5 times 0 plus 0 squared over 2 plus c is 12. So that just means that this goes away and that goes away, so c is 12. So the height after t years is h of t is equal to 1.5 t plus t squared over 2 plus 12. And then we want to know how tall are the shrubs when they are sold. And they're usually sold after 6 years, so we want h of 6, which is 1.5 times 6 plus 6 squared over 2 plus 12, which is 39 inches. So they're usually 39 inches when they are sold. so that is the end of this video. I hope that you enjoyed this section. Alright, so I thought that I would do an extra example of an integral involving cosines and sines, alright, just so that you have another example of these trigonometric functions. So this is one right here where I can break this integral of 5 cosine of u plus 4 over sine squared u du into two integrals. So let's make it 5 cosine of u over sine squared u du, and then 4 over sine squared u du. Alright, so this is 5, and then we have cosine of u over sine of u, and then 1 over sine of u. So that's still 5 cosine of u over sine squared of u du plus 4, and that's 1 over sine squared of u du. Alright, so cosine of u over sine of u is cotangent of u, and 1 over sine of u is cosecant of u, and then 1 over sine squared of u would be cosecant squared u. So if we use the integral rules, this is minus 5 cosecant of u, and then this would be 4 times a negative cotangent of u, and then plus c. So we're left with negative 5 cosecant of u minus 4 cotangent of u plus c. So I just wanted to show this extra example to show how that technique of splitting up this fraction into two separate integrals could be applied to problems with trigonometric functions as well.